Welcome to This Explainer. Today, we're embarking on a journey into something truly mind-bending. We're diving into the abstract, structural grid that secretly dictates the shape of absolutely everything in our physical universe. Think of it like stepping into a cinematic, almost sci-fi world of differential geometry. And hey, this isn't just about staring at dense formulas on a chalkboard. It's about actually understanding the invisible mathematical scaffolding of reality itself. By looking at how surfaces are spun, stretched, and constrained, we're going to unlock the fundamental rules governing the entire universe of shapes. So get ready to see the space around you in an entirely new dimension. To really wrap our heads around this, I want you to imagine just for a second that you're a tiny bug, and you're placed on a perfectly smooth shape. Now, as this bug, you are bound entirely by your immediate horizon, right? You can crawl around, look left, look right, but your field of vision is incredibly small compared to the sheer vastness of the object you're actually standing on. So how could you possibly know the global overarching shape of your world? Well, this perfectly illustrates the main tension at the heart of differential geometry. The profound difference between local geometry, which is what our little bug experiences, and global geometry, which is what the entire world actually looks like from the outside looking in. It's kind of like how the surface of the Earth appears completely flat to an observer who can only see up to the horizon. Our bug feels like it's navigating a perfectly flat grid, totally unaware of the magnificent, warping architecture happening in higher dimensions all around it.
Okay, so formally speaking, a surface is defined as a subset of 3D space that locally resembles a flat 2D plane in the vicinity of any given point. Basically, whether it's a sphere, a cylinder, or some unimaginably complex twisted force field, if you zoom in close enough to any single point, the math just flattens out. It starts to look and behave exactly like a standard two-dimensional plane. But differential geometry asks a much deeper question here. How do we mathematically weave all these endless, flat, local grids together to map out the sprawling, curving structures of three-dimensional space?
Well, that brings us to the core constraint. What exactly makes a surface compact? Let's take a look.
So we can perfectly contrast these two distinct realities. For a surface to mathematically be considered compact, it absolutely has to meet two strict criteria. It must be closed and it must be bounded. Think of a sphere. It doesn't just shoot off into infinity, right? It's bounded within a finite region of space. And it contains all of its boundary points, meaning it is completely enclosed. On the flip side, we have non-compact shapes. Take an infinitely stretching plane. That's unbounded. It literally just keeps going forever. Or think about an open disk, which is basically a flat circle that's missing its exact outer edge. Because that absolute edge is undefined or open, it's not closed, and therefore it's not compact. You can think of compactness as the ultimate mathematical containment field.
Which leads us perfectly into the compact surface zoo, where we start classifying this entire universe of shapes.
Now, the really crucial point here is this surprising sort of cheat code of the universe. Despite the infinite complexity you might expect from all these crazy shapes, every single compact surface can be reduced simply to how many holes it has. Mathematicians call this number the genus. If your shape has 0 holes, so a genus of 0, it's fundamentally just a sphere. If it has 1 hole, a genus of 1, it's a torus, which is basically a donut shape. And if you have a genus strictly greater than 1, well, it is simply a series of joined tori, basically just multiple donuts mashed together. And that's it. Up to smooth deformation, every single compact surface in three-dimensional space falls neatly right into this incredibly simple classification. It is just such an elegant, hidden order underlying all these complex geometries, because a compact shape perfectly separates a bounded, finite inside from an unbounded, infinite outside, you get this really clear separation. And because of that, you can unequivocally define which way is out at any given point on the surface. You can assign a smooth, outward-pointing unit normal vector everywhere across the shape. So what's the profound conclusion here? It's that every single compact surface is orientable. There is absolutely no ambiguity. You could never construct a one-sided, non-orientable shape like a Klein bottle that exists strictly as a regular, non-self-intersecting compact surface in standard 3D space. The math literally just won't allow it.
All right, let's shift gears a bit and look at the rules of curvature and how we actually go about bending the grid.
There's this rule, proposition 8.6.1.
and it states that if you have a compact surface, there must be at least one point on it where its Gaussian curvature is strictly greater than 0. Now, why does this actually matter? Well, think about it physically for a second. Because a compact shape is bounded, it can be entirely enclosed inside a massive imaginary sphere. At the exact point where your compact surface pushes out and gently touches the inside of that bounding sphere, it has to be curving back in on itself in all directions just to stay contained. It cannot be saddle-shaped there. It absolutely must have positive curvature. The strict requirement to stay finite mathematically forces the grid to bend positively against its boundaries. It's fascinating. So, bringing this all together, let's look at the big geometric picture. The exact intersection where curvature meets topology. Here is where it all finally collides. We have this theorem, Theorem 10.3.4, and it dictates that a connected, compact surface with constant Gaussian curvature absolutely must be a sphere, period. It's like if you tell the mathematical grid, hey, you must be closed, you must be bounded, and you must bend exactly the same way at every single local coordinate, the universe literally has no other choice. It forces the geometry to resolve into perfect spherical symmetry. You cannot have a constant curvature donut. You cannot have a constant curvature multi-hole shape in 3D space. The global restriction of compactness, colliding head-on with the local restriction of constant curvature, leaves only one possible architectural reality, the sphere.
I want to leave you with a provocative thought to ponder today. As you go about your day, just look at the bounded, solid objects around you. Everything from the coffee mug on your desk to the very planet we're standing on is secretly governed by this invisible differential grid of reality. The local bumps and curves are inextricably linked to the global destiny of the shape itself. So what other hidden mathematical constraints are quietly dictating the structure of our world, just waiting for us to uncover them? Thanks so much for joining me on this explainer, and keep exploring the geometry of your reality.